So welcome to lecture number 31. Finally, we are now at a position to understand the hydrogen atom. So in this lecture, we are going to take on how to solve the Schrodinger equation for the hydrogen atom, and it would give us the energy levels of different orbitals associated with quantum numbers. So first of all, let's start with a statement that the Schrodinger equation for hydrogen atom can be solved exactly. Okay, so you might be wondering that why I have written this statement. In fact, hydrogen atom is the only situation, or is the only real atom where the Schrodinger equation can be solved exactly. So what happens with the other atoms? So obviously the Schrodinger equation can't be solved exactly for those atoms. We will come to that questions, why not, and then how did we come to know the energy levels of the orbitals of other atoms. That we will come, we'll address it at a later point. So now, having known that, so why we concentrate, or why we try to learn the details of hydrogen atom? The main reason that because the hydrogen atom serves as a prototype for other atoms and molecules. Okay, so that is the main reason. Excuse me for a second. Okay, so now we begin with the hydrogen atom, where we understand that the hydrogen atom is based on a model, a positively charged nucleus, okay, and there is one single electron over here, and this single electron is moving randomly around any direction around the nucleus, okay, and it is subjected to some potential energy, okay, because it is under a force field, and we all know that the force field is electrostatic in nature, okay. And not only that, this electron is moving, so this electron also contains kinetic energy, okay. So as we have already mentioned earlier, that this rotating electron or moving electron around nucleus, so this concept is based on a diatomic rigid rotor model. So we can think that this is a kind of a diatomic rigid rotor, albeit with a difference. The difference is the separation between electron and nucleus is variable. So this is represented by the vector r. Whereas in diatomic rigid rotor, this distance was fixed, so we eliminated any radial part. So here the radial part is important because this is the variable part. Now, other than the radial part, the angular part is exactly the same with the diatomic rigid rotor. If we think that we fix the nucleus, so there are two major features that I'm going to write. Number one, that the nucleus is basically the proton. So the proton is fixed at the origin of the spherical coordinate. Of course, why we introduce the spherical coordinate here, very simple, because this is a same thing as a diatomic rigid rotor, and it is dependent on the theta phi, the angular part. Now, since the angular part is the comparable with a diatomic rigid rotor, the theta phi part would exactly behave the same way, all right. So the second part is that in diatomic rigid rotor we considered a reduced mass. The same thing here. So we now represent the reduced mass as mu, okay, and definitely this is can this is represented as mu p multiplied by mu e divided by mu p plus mu e. Okay, so what we think is now this is a model. This is a fixed at the origin of the sphere. Proton is fixed at the origin of a spherical coordinate. Electron is moving around it under a potential field. It has a potential energy as well as a kinetic energy, and the reduced mass of electron and proton is represented by mu. All right, so we will start with the Schrodinger equation. So definitely, as we have learned earlier, this is the time independent Schrodinger equation. We are going to write h psi. So now psi is dependent on theta, r and phi is equal to E psi r theta and phi. So except the r part, the theta phi part is exactly the same as of the diatomic rigid rotor. All right. So now we have to express the expression for the Hamiltonian operator. So Hamiltonian operator is the total energy operator, of course. So this stands for the kinetic energy operator plus the potential energy operator, and we all agree with this, right? So this comes from our basic understanding of Schrodinger equation. So the question is, what is the kinetic energy operator here? So we know that the kinetic energy for one dimension is minus h cross square divided by 2m, and then d2 d2 psi dx2, right? So here, remember, this is a three-dimensional system using spherical coordinates. So therefore, we are going to write h as minus h cross square divided by 2 mu, and we write the Laplacian operator. Okay, so this is dependent on x, y, z in Cartesian coordinates and r theta phi in polar coordinates. Okay, and plus the potential energy operator. So here the potential energy, we will try to find the expression later on, but here for the time being we just write u as a function of r, because this is the electrostatic is in nature, so it only the variable is the separation between proton and the nucleus, provided that the charge of proton and the charge of electrons, those are constant. So this is our Hamiltonian operator. We already got it. So now we have to frame the Schrodinger equation first following this expression, and then we may make an attempt to solve that. Okay, so here everything is all set for us. So now I'm going to clean the board, and we will start from here with the with framing the exact Schrodinger equation. Okay, so let's work it out. Okay, so I have written once again the basic Schrodinger equation. This is the kinetic energy operator, and this is the potential energy operator. Those are getting operated on psi is equal to giving the total energy E multiplied by psi. So now, for the sake of simplicity, I'm not going to write within bracket r theta phi every time. So whatever psi I'm going to write to represent the function of r theta phi. So I'm only going to use the symbol psi. So therefore, or we have to elaborate this equation now. So minus h cross square to mu. So now we have to represent the Laplacian operator in polar coordinates in terms of all r theta and phi. So if you remember those long expression, so I'm going to write over here. So this is denoted as 1 over r square del r of r square del r. Okay, and So if I include psi in here, so this is psi plus 1 over r square sine theta, then del theta of sine theta, del theta or del psi del theta, plus 1 over r square sine square theta del 2 psi del phi 2. Okay, so I'm going to close my bracket plus u of r psi is equal to e psi. Okay, so now you see I have written the entire expression in terms of the polar coordinate. So now this equation to be modified into a bit simpler form. So how we can do that? So let's multiply by so here we have the r square at the denominator everywhere, and here we have 2 mu. So let's multiply by 2 mu r square on both sides. So let's write it here, that multiplying 2 mu r square both sides. Okay, so if we do that, what we get is actually, or let's write minus h cross square del r square del psi del r. Okay, so plus we have so the r square term would be eliminated, and so I still am going to write plus minus h cross square. So I'm going to keep the bracket, so 1 by sine theta del theta of sine theta del psi del theta, plus I have 1 over sine square theta del 2 psi del phi 2, and then what I can do is I can take this e psi part inside, so I have plus 2 mu r square multiplied by u of r minus e, and that is multiplied by psi. We can write it because this potential energy operator is multiplicative in nature, so we are just multiplying it, so that's why we can write that part. So this becomes is equal to 0. All right, so having written that, so you may ask that why have I written something like this, okay, with plus and then minus, okay, something like this. So now in the next step things are going to be a lot clearer. Why? So now let's rewrite the above equation, or minus h cross square del r of r square del psi del r, plus, can you recognize this expression? Yes, it is the L square operator for the dynamic for the diatomic rigid rotor. Okay, so if you have forgotten, then you please go back and study the lecture of that chapter. So this belongs to that L square operator. Okay, so L square psi plus, then we can write 2 mu r square u r minus e psi is equal to 0. Okay, so now you see this equation looks much simpler than this equation, and not only that, if you look at this, then you see that this is a function dependent on r only. Now this is also the function dependent on r only, and here this part, as we have already seen, this is the function of theta and phi only. So what do we get? That this part is already a variable separated partial differential equation. All right. So now it can be solved using our standard technique of the method of separation of variable. Okay. So how we can do that? So of course, the same technique we are going to follow, that we have to express psi as the product of few independent functions. Okay. So let me erase the rest, means the top portion of the blackboard, and I'm going to write the exact same equation over here, and we want to proceed further. Okay, so let's do that. Okay, so we will continue from the same point. So I have written the last part of the equation at the top of the board, and now, as I have already mentioned, that this is the variable separated method equation. So now we can think that let psi r theta phi is equal to the product of three independent functions. One function is the function of r only, radius. This is called the radial part or radial function. So we represent it by uppercase r, and multiplied by function of theta and phi. But remember, that part has been already solved. So we can directly write that this is nothing but the function of spherical harmonics. Okay, so that means ylm theta phi. So if that be the case, so here we once again would like to draw your attention that if we operate L square on psi r theta phi, so it becomes L square getting operated on r and ylm theta phi. All right, so this r part is constant, so it comes out rr, and then L square on ylm theta phi. If you remember, this is an eigen value function, and it gives you our eigenvalue equation. So it gives you the eigenvalue h cross square L times L plus 1 multiplied by ylm theta phi. All right, so we have no doubt about that, this part. So now we are exactly going to use this relationship over here. So now, or we just replace psi with this ylm theta phi. So let's going to write. So since this is a partial derivative with respect to r, so ylm theta phi part comes outside. Okay, so ylm theta phi part comes outside, then it becomes the simple derivative ddr of r square d of rr dr. All right, plus, now instead of L square psi, we can directly write this. So rr, and we have h cross square L times L plus 1 ylm theta phi. Okay, so everyone, can you follow that? So plus, we have once again 2 mu r ur minus e, and instead of psi, again we are going to write rr and ylm theta phi, and that is equal to 0. Okay, so now we have this equation. So once again, what we should do now, we would divide the left hand side by rr ylm theta phi. So that's what exactly we do. Okay, so if we do that, so the thing that we get is actually Okay, so or all right, so this part is getting a little bit crowded here. So I'm going to write this part, and just once again I'm going to rewrite the equation, okay, to make it look better. Okay, so we'll just resume with the equation. So you see, since this was a quite long equation, so it's better to write it freshly. So still you see I could not manage to fit the entire equation within the one single line of the board. Anyway, that doesn't matter. So we have this equation now. So we see that we have this ylm theta phi part appearing everywhere. Okay, so we can easily get rid of that ylm theta phi part and we can rewrite this equation. So now you see also you have this radial part over here, this radial part over here, and this doesn't have the radial part over here. So it doesn't matter whether you divide everything by r of r, because then this part will become free of r, but then this part here we have r of r as the denominator. So this entire thing would still become a function of r. Okay, so that's why what we should do is, or let's rewrite minus h cross square. Let's eliminate these ylm theta phi part. So we can write h cross square ddr of r square dr plus rr h cross square l multiplied by l plus 1 plus 2 mu r square ur minus e r of r is equal to 0. Okay, so now you see we have an equation. Okay, an equation which is the function of the radial part r only. So if we solve that particular equation, we would be able to find out the rr part, and of course the ylm theta phi, that means the spherical harmonic part, has already been solved. So just by solving the function of r, we get to know the entire psi, that is the psi r theta phi, that is the solution of the Schrodinger equation. Okay, so you see that in some textbook this equation was modified a little bit, okay, to make to resemble a standard form. So what modification they do is actually, once again they divide the left hand side by this 2 mu r square. So if they do that, so it looks something like that. So or so this is a pretty standard way of representing this entire radial equation, plus so we have divided this part by that, and of course we have this 2 mu part should come over here. So h cross square l, this divided by 2 mu, and then so that the 2 mu okay, so the 2 mu r square part will be over here. So the 2 mu r square part will not be over here. So plus u of r minus e. So now what we're going to have, that we are having this rr part on both of the terms. So we take that common of r of r, and that becomes is equal to 0. Okay, so now you see you have one equation which is only is represented only as a function of r. All right, and so this equation therefore is called the radial equation for hydrogen atom. So we have to solve this. And why did we write in this form? Because this form resembles a certain standard equation which we can solve. So like you remember the situation for the diatomic rigid rotor, or the situation for simple harmonic oscillator, we took the help of certain standard polynomial, okay, or series method to have the solution. So like we have the Hermite polynomials, Legendre polynomials. Exactly in similar fashion, we will have a new type of polynomial. So you have to take the new type of polynomial for solving this equation by once again series method. Okay, so we are going to discuss the solution of this particular radial equation in the next lecture. But remember once again that here the total kinetic energy, remember, is a summation of uh, the linear kinetic energy, okay, plus the kinetic energy due to rotation, okay. So this part, okay, whatever, has already been taken care of during while we have solved the spherical. Okay, so the total energy, similarly, we have the linear kinetic energy plus the kinetic energy due to rotation and the potential energy. Okay, so here we stop, and we will continue our lecture in lecture number 32, where we are going to solve the radial equation for hydrogen atom. So see you in the next lecture. So till then, goodbye.